In AP Chemistry. In today's mini lecture, we are going to be looking at the equilibrium expression and how to solve for the pH of weak acids. This is actually an AP concept rather than just a honors concept. So we've never done this before, so I'd like to explain it and work it out for you. So first of all, what we need to do is we need to look at a strong acid versus a weak acid. In a strong acid, you have 100% ionization. That means when you put it in water, every single one of those hydrogen ions break apart, dissolves in the water, and contributes to the overall pH. Well, a weak acid, by name, weak, means that it is going to be less than 100%. Usually, it's going to be somewhere less than 5%. So what we have to do, based on the percentage of ionization, how much it dissolves, we have to determine how many actual hydrogen ions are in the solution that will contribute to the pH. So in order to do this, I have a note set for you. The first part of it talks just about determining the equilibrium expression. The second page is going to be a table that gives you the Ka values. And then finally, the third page is going to be how you actually calculate it. So I have worked a problem out completely for you on your notes, but I didn't do it step by step. I just wrote everything down. And then I asked you to do a practice problem down here at the end. And that practice problem is the problem that I'd like to do for you in today's mini lecture. So we use what is called the Rice method. And the Rice method means do the reaction, do your initial concentrations, change in the concentrations due to ionization, and then finally what happens at equilibrium. So when you do this, you are going to always be dissolving your actual weak acids. So we're going to write this down as what happens when you add it to water. So this is my reaction. And it's not going to be like a chemical reaction where you get different, it's ionization reaction, like how it dissolves. So first of all, I'm going to get an H3O on this side. That's that one hydrogen from right here. And then I'm going to get a C6H5COO. Now, if y'all remember the COOH, that is our CO group, and that represents a organic weak acid. All right, so this is going to be our ionization, how it dissolves. This is your acid, this is your base, conjugate acid, conjugate base. So now let's go through and look at the initial concentrations. So the initial concentration says that I have 1.50 molarity of the original weak acid. The water is just water, so we omit it. The hydrogen ion concentration, we don't know that, but we do know that its original was 0. And this original was 0 because nothing happened. It wasn't in the water yet. So how's it going to change? Well, whatever amount of these that do dissolve, we're going to call X. Whatever amount that dissolves on this side, we'd subtract it from it, and then it would add to this side. So this would be plus X, and this would be plus X, because these are at a 1-to-1 ratio. So what do we end up with? Well, we actually end up with 1.50 molarity minus X, and that's going to be an X, and that's going to be an X. So this is going to be our final equilibrium concentrations. So how do you write the equilibrium expression? Well, the equilibrium expression is also referred to as K. Now, this can be a Ka, and that would be an equilibrium expression for an acid. That's what we're dealing with. It could be Kb, equilibrium expression for a base, or like we did in honors, it could be Keq, equilibrium expression for just a aqueous solution. So what is the actual equilibrium solution? How do you determine what the equilibrium expression is? It's going to be the concentration of my products over the concentration of my reactants. So these are the concentrations here. So when I look at this, I get my Ka to be x squared on the top, and then on the bottom, do you see this x right here? Now, on this particular problem, when you have an x like this, and it appears in the bottom, then we're going to assume that this is going to be a very, very, very small amount of ionization. We're talking like 1.2 times 10 to the negative fifth. We're talking really, really small. So compared to this 1.5, it is real, real small. So we just omit that entire x right there because it's so small it's going to round off. So I end up with this right here. So now what ends up happening is I have my equilibrium expression for Ka. Well, if I know what Ka is, you say, well, how do you know that? One of two things. It's either given in the problem, 6.4 times 10 to the negative fifth, or you look at your reference table, and this table will always be given to you. So you can find it one way or the other, and you'll see that the Ka is, and I'm just going to put 6.4 times 10 to the negative fifth is equal to, and then that's going to be x squared, 1.5. So now I'm going to go about solving for my x squared. So I get 6.4 times 10 to the negative fifth. I'm just going to have to work this out. 6.4 times 10 to the negative fifth, and that's going to be times 1.5. So I'm going to end up with 9.6 times 10 to the negative fifth. So now if I take the square root of that answer, so I'm going to try to find square root of 9.6 times 10 to the negative fifth. I end up getting 0.00980. And I like to use three significant figures. So this is my x value. So what is x value? X is the concentration of hydrogen ions. So even though we started with a concentration of 1.5, only a few of them actually dissolved. So we only actually get 0.0098 dissolving. So this is the number of hydrogen ions that will contribute to the pH. So when I come back down here to solve for the pH, instead of me using, like in a strong acid, the concentration of the solution, I'm going to use the concentration of the X value that I found. And when I do that, that will give me the pH. So now I'm just going to simply say negative log of 0.0098. And I'm going to get an answer of, for my pH, 2.01. And that is going to be how you determine the pH. Now, there's one last thing that I want to do. Remember I told you about this dissolving and not dissolving at 100% because it's a weak acid? We need to determine what it does dissolve at. What is the percentage? Well, guys, percentages are always part divided by whole. So we come down here, and I've already written down the percent of ionization. Your percentage of ionization is going to be equal to the concentration of the ions divided by the concentration of the acid times 100. So all I have to do is to say my percent of ionization is going to be equal to the concentration of the ions, that's my X value, 0.0098, divided by the original concentration, which was 1.50, all of this times 100. And that gives me my percentage of ionization. So I'm just going to go back in and check that. So it's got 0.0098 divided by 1.5, and then I'm going to multiply it by 100. When I do that, I'm going to get 0.653%. Now we look at that and you say, is that a correct, acceptable answer? Well, I told you it'd be somewhere below 5%. This is very, very low. What that means is when it has a real low percent ionization, that usually refers to a very, very weak acid. And the higher percentage it dissolves, then the stronger it becomes. And when it reaches 100%, it is a strong acid. So I have created a worksheet that follows along with these notes, and it does, the first 3 problems are just like this one, and then the next 3 problems uses the percent ionization. So I would like for y'all to use these notes, and again, I'll post them online, and then I'd also like for you to work on that worksheet. And as you work through the worksheet, if you have any questions, as always, just give me a remind me. All right. Thank you.